students. So this is a class where we will be talking about balancing of reciprocating masses. Now we have, the reciprocating one will move in horizontal direction, okay, in this manner or vertical manner. Okay, this like this and like this. Okay, so when this type of to and fro motion, okay, causes some unbalance, then we will have to balance that part of the reciprocating mass. So here one example we have taken, that is using slider crank. So here this part is called the crank, this part is the connecting rod, and this is the slider. So if this moves in this direction, suppose the crank, okay, then the slider will tend to move in this direction, okay, in this direction, right? So let's find out that force first. Now if we have a mass here, okay, m, at a distance of r, the crank length is r, okay, r. So the value of centrifugal force of this will be what? This direction, m r omega square. Okay, so if we find its component, so m r omega square, the component will be this one and this one. Okay, so this one will be m r omega square cos theta. Okay, so this is what we have written, and this one will be m r omega square sin theta, this part. Okay, we have written that here, m r omega square cos theta, right? And you see, this is actually the unbalanced force. Okay, unbalanced force, or this force is what causes the oscillation. We call this primary oscillating force, right? This you just have to understand. So this is the force, it has come from the component of the what? Centrifugal force here, right? This one. And we have found that this causes some oscillation. Okay, oscillation. Now what type of unbalance it causes, or is there any other type of unbalance? We'll have to see. Now see, this is the unbalanced inertial force we call. Okay, so first we will write down the ratio between this connecting rod length and crank length. So let's this length we have taken as this crank length as r, and this length from here to here, the connecting rod length, okay, this let's take it as L. So L by R, we assume it as L by R, we'll just write it as N. Okay, so whatever value of length of the connecting rod divided by length of the crank will be a number, that is N. Okay, so it has been found that the total unbalanced force in a reciprocating example in this manner, suppose this is the Sadakin mechanism, is that addition of primary unbalanced force plus one extra force, that is m, okay, sorry, m r omega square, okay, cos twice theta. It's not unable to write. So m r omega square cos 2 theta. This theta is now this angle. Okay, theta varies from 0 to 360 degree, it goes on. So divided by this n that we have found, length of this connecting rod divided by length of the crank. Okay, so so we will have to combine them together, and that is a total unbalanced force. We see, this is the force, and this force causes the this force is required to accelerate the mass. So in this case, actually the mass is here. The thing is here, ultimately we have to accelerate this part, okay, this part, so that we in that case we have to take the component of the centrifugal force of the mass here. This is the mass. So this is m r omega square cos theta plus m r omega square cos twice theta by n. Okay, so this is called the secondary part, this is called the primary part. M r omega square cos theta, this is the primary oscillating force, and m r omega square cos twice theta by n is the secondary oscillating force. So when we combine them together, there's total oscillating force that causes the oscillation of this slider. Now this is the thing. So m r omega square cos theta plus m r omega square cos twice theta by n. So you have seen that this is called the primary accelerating force, and this is called the secondary accelerating force, right? Okay. Now their values will be maximum when cos theta is 1. Okay, minimum is the whole thing is 0, and you see cos theta can take cos or sine, both can take a value of -1 to +1. So maximum one maximum will be when this is 1. Okay, cos theta becomes 1. So when theta is 90 degree, when theta is 90 degree, this is mr omega square. Okay, cos theta cos 90 is 1, and this is mr omega square. This is if we put this as 90 degree, this is cos 20, this is again 1. So this is mr omega square n. Okay, so here now sorry, this is actually this will be 90 degree. They will be at 90 degrees to each other. This is at 45 degrees, so that this becomes 90 degree. So their maximum values will be when this part becomes 1. Okay, cos twice theta becomes 1, and here cos theta becomes 1. So we have their maximum values, right? Okay. Now for very slow running engines, this part is neglected. We only take this as the couple or sorry, this as the reciprocating unbalanced force. Okay, sorry, not this is not the unbalanced one right now. We call this as the accelerating force that causes the acceleration of this slider. For slow moving engines, we neglect this term. We only have this term. Okay, so this what we have. Now we will have to see what are the. Now we'll focus on the primary accelerating force acting upon the slider. Now we will draw a free body diagram of the slider. What are the forces that we have? Now with respect to, these are actually the forces of link 2 with respect to link 3. Similarly, forces with respect to forces of link 4 with respect to link 3. Okay, the directions are like this. Why? Because you see you have the instantaneous center of rotation between these two as here. Okay, here. Okay, and you see that link 2 is moving in this direction, which is pulling this link 3 in this direction. So their I center or instantaneous center is here. Okay, and the force between them can be passing through, we can take it as passing through between the I center of these two. Similarly for 3 and 4, I center is here. Okay, so the force will be passing through in this through their I center, instantaneous center of rotation. So here you know that this, let's say this part, okay, the slider is moving in this direction, so it will pull the link 3 in this direction, in this direction. So ultimately their centrifugal force passing through this point can be taken in this direction. So actually F43 is the force of acting on link 4 with respect to link 3. Here F23 is the force acting on link 3, which is sorry, the force acted by link 2 on 3. This is force acted by link 4 on 3. Okay, similarly here you see force acted or force which is caused by link 4 on link 1. One is link, that is a fixed link, is link 1. Okay, here also this is link 1, here also this is link 1. Okay, so we will have this as vertical. Why? Because the slider is just kept on the here due to gravity or whatever you say. This is actually the instantaneous center is at infinity. Okay, here, and in this case the direction will be in this case, in this direction. Okay, so that is the centrifugal forces. Yeah, these are the centrifugal forces. Here again, you know, here this is the, I'm sorry, these are not centrifugal, this is centripetal force in this case. So now we have taken F21 actually in this position. Actually this is a this is the position now. This is not at this position, and the crank is here, and we have the slider here now. Okay, here. Okay, this is the position, and here we'll have the have a value of F, okay, force of 2 with respect to 1. There is a centripetal force towards the center, and here you know this link 4 and link 1, the centripetal forces will always be vertical in this case. Okay, F4. So F21 and F41 we have taken. Okay, so this is the because slider is linked with your crank, that's why we have to show it together, and they are linked commonly with link 1. Okay, so link 1 is here, link 1 is here also. That's why we have shown this F21, this force, and F41 in this force. Let's find the component of F21. and write them as vertical F21V and F21H. Okay, so this is F21V we have written, and F21H. H is the horizontal component. Now you see horizontal component is there. This is the force, okay, which is not cancelled by anything else. So this will cause uh, uh, this fixed point to shake like this. This is called a shaking force. Okay, in this direction it shakes. Because see, I mean, one more thing, you can see this is acting in this direction. No, after some rotation, when this F21 force becomes the opposite, then it will act in this direction. That's why this F21 is not balanced, and it will cause a shaking force in this case. This is called shaking force. Okay, and you see F41 is in this direction, F21 is in this direction. They are causing a couple. Okay, this is called shaking couple. Okay, and you know shaking force causes a unbalance in this direction. This is called shaking force unbalance, and the shaking couple in this direction will cause an unbalance like this. Okay, vibration of this kind of thing. So we have two things to balance here, right? So how to balance them, that is what you need to know. This is what we have written. See, this is shaking force is written here, and shaking couple is also written. Please read and go through it. Now see how to balance the shaking force. Actually we cannot balance completely. This is very important. The shaking force cannot be balanced completely. This we have to actually, by trial and error, actually we have to minimize it. How can we minimize it? Just by adding a counter mass. So actually, you know, this you have seen in IC engines that we use a mass like this, counter mass. Okay, so to balance the rotating mass, see here, you know, this is the mass that we have taken. No, this is the mass. So you have to place a counter mass here to at a distance, some distance r. We have to find out. Let's say this is MC1, and we'll place it at RC1. Okay, so we have to find out RMC1 and RC1, and we'll place the counter mass. That is for rotating mass. Now we are talking about reciprocating mass. No, so we have to balance this shaking force also. For the shaking force, what we do, we have to add additional masses to this. Additional mass. Okay, some more mass to this one only. So here only we will add some more mass to this. More mass here, more data. Okay, so that is additional to the counter mass that we place. See, it is written. So to balance the shaking force, what we do, rotating counter mass at the radius is added directly opposite to the crank to balance the shaking force. This mass is additional, is added in addition to the mass already added to balance the rotating unbalance due to mass of connecting rod piston assembly. So you have known that one mass is for rotating part balancing, and one extra mass is added for reciprocating part balancing. Okay, that is how we balance the shaking force. And one more thing, this shaking couple, okay, shaking couple is actually they get balanced. So you see, normally this is how, for the beginning, at the beginning this is the couple, and the next part, when it comes in the opposite direction, no, this direction, then this will be, they will I mean, there is no couple in this case. This will always be vertical only. Okay, and what you can say that the slider is actually in between these two guides. Okay, there is one actually this type of actually it is enclosed. The slider is enclosed between some closed your some kind of link. So this slider cannot go up actually. It cannot go up or down. It can only slide. Okay. So when this force, this F21 gets in the opposite direction, there will be an opposite force here because of the, because of it, it will not allow it to move upwards. Okay, so that's why there will be an opposite couple now. Previously this was the couple. Okay, after this rotates here, there will be an opposite couple. So this, okay, shaking couple, they balance each other. Why? Because you see, it is written shaking couple produces an oscillatory vibration. This is okay, but the shaking couple gets balanced on its own, right? Here you see, uh, it's actually written. So hence they balance each other. See, this vertical forces and this one, these two forces are opposite. They balance the forces. Okay. But a couple actually, let me tell you in a simple manner, these forces they get balanced where because they are in opposite direction. Once this becomes opposite, the other one becomes again opposite to this. This one and this one cancel each other. This one and this one cancel each other. Okay, so that way they balance each other. That is what is written here. Okay, now the shaking force, how to balance it? We have to place another countermass additional to the rotating countermass. Okay, this is what is written here. Now, since we cannot balance the shaking force completely, okay, we cannot completely balance. What to do? A portion of the mass only is balanced. Normally, what we do see, we take 2/3 of the reciprocating mass to be balanced. Okay, so whatever reciprocating mass we have, that causes what type of primary force you see? The primary force here is this one, mr omega square cos theta, and this is the secondary force I told. So primary force, okay, is not completely balanced. This is balanced only 2/3 of this. Okay, that means around 75% is balanced. Okay, so for that, how to balance it? You see now, you have to take the maximum value of unbalanced force, that is mr omega square, maximum only, because the others, if we balance the maximum value, whatever is less than that will get automatically balanced. So maximum primary force is this. We have neglected the secondary one because we can neglect it for slow engines. We have assumed it that it is a slow engine. So mr omega square is what we have to balance here. Okay, so 2/3 of this one we have to balance. Okay, now actually that is not always 2/3. So you see, we can either take 2/3 or a value between half and 3/4. Okay, this also can be done. Okay, so that is actually half of the mass only. So if the mass is 2 kg, we take half of that, that is 1 kg, and 3/4 of that. 3/4 of this 2 will be around 1.5. So 1 to 1.5. Total mass is 2 kg, but we balance 1 kg to 1.5 kg. We don't completely balance the 2 kg. We cannot do it actually. Okay. So for that, we take a ratio in between half of the mass to 3/4 of the mass. Okay. So actually, we usually take 2/3, but we can also take between half and 3/4. Okay, so let's take this term, this as c can be half also. Okay, okay, c can be 3/4 also, c can be 2/3 also, c can be anything between half or 3/4. This value of c is the fraction of the mass that is balanced. So if the total mass is 2, if c is half, so what is the fraction? Half fraction, 0.5, 50% is balanced. Okay, so that means out of 2 kg we have balanced 1 kg, that is half is the fraction of mass balanced. Understood? If suppose 2 kg is the total mass, we have balanced 1.5 kg out of it. Okay, so how much we have balanced? 3/4 of the total mass we have balanced. Okay, in that case c will be 3/4. So c is a fraction of the balanced mass we take. Understood? So you see, since we have balanced the c portion of this mass. Okay, sorry, the mass, the force will be, see, mass and force are different. These are a lot of confusing things here. We have considered cos theta because we have to balance it at any angle, right? So maximum will be mr omega square. That's fine, but at suppose any angles are 10 degree, 40 degree, 30 degree, whatever. So that's why we have considered cos theta. So we have seen that the unbalanced force was mr omega square. We don't completely balance it. We balance only a portion of it. So the fraction is c. So let's say c is half, then half of it. So you multiply c with this, because if c is half, so half of this force will be balanced. If c is 3/4, 3/4 of this force is balanced. Okay, and in between that any value c can take. So we have balanced actually balance this primary force, only a fraction. What is a fraction? C. So C portion of this, that means C multiplied by this whole force is balanced. What is the remaining one? Remaining one will be 1 minus C into this. Okay, because you see 1 minus half is half. So 1 minus 3/4 is the remaining part, isn't it? If 4/4 is there, that is 1. If 2/2 is, that is 1. Okay, so that means the total is 1 minus the balance portion. So 1 minus half is what? Half portion is remains. So let's take this example. 2 kg, out of 2 kg we have balance 1 kg. That means half we have balance, and remaining one is what? Half. So out of 2 kg we have balanced 3/4 of this. 3/4 of 2 kg is 1.5 kg. We have balanced. Okay. So 1.5 kg of balance means what is the remaining part? That is 1 minus 3/4. Okay, isn't it? 1 minus 3/4 is remaining. That is what is remaining to be balanced. Okay, that means here see 1 by 2, 3 by 4. These are C only. This fraction C. So we have balanced the fraction of this force and to a fraction of C, and the remaining force will be 1 minus C into this force. Okay, this remains unbalanced. Okay, we have to minimize the unbalanced part. Okay, so that we can, up to the maximum extent we can balance this force. Okay, primary force. Understood? This is what where this is very important. And mathematically how to do it, you see particle component of centrifugal force which remains unbalanced is this. Okay, see this part we have to balance. Actually this part we have to balance. This is the vertical one, particle in this direction. Okay, so and the horizontal part we have to find out, and the horizontal part of this will be what? If we multiply yeah, actually just a moment, just this is we have written unbalanced, no? So sorry, this is not C, this has to be 1 minus C, 1 minus C, 1 minus C multiplied by, that means instead of, in place of C, this has to be 1 minus C, sorry, so this is a mistake. 1 minus C. Okay, actually this we have to take this one. By mistake I have written the C. Actually this is 1 minus C because this is unbalanced, no? Unbalanced. So this remains unbalanced. So this is 1 minus C into mr omega square cos theta. Okay, this is the vertical component, and the horizontal component of the unbalanced force will be actually of this one, component of mr omega square. Let's just simply take it like this. You see, again, actually, yeah, this is correct. 1 minus C mr omega square cos theta. Again, I have to tell you here a lot of mistakes has been done. This is not vertical. The horizontal component is cos theta, no? So this has to be horizontal component of unbalanced force. So this actually has to be, this word has to be horizontal component, and this remains unbalanced is 1 minus C into this. This is actually horizontal. And obviously the vertical component will be the balance part, this mr omega square cos theta. So this is the mr omega square cos theta is the horizontal component, and what is the vertical component of this? Mr omega square sin theta. Okay, so the portion that we have balanced it is multiplied by C. Okay, C multiplied by this one. So that is what we have balanced. So by squaring the horizontal component and vertical component, we can get the resultant unbalanced force. Unbalanced force. Okay. So here we have to get the resultant unbalanced force at any instant, because we have taken the angle. Okay. If we take this sin theta and this cos theta as 1, then we will term this as maximum unbalanced force. So in this case, the unbalanced force can be minimum if we take C as half. That's why we start with half of them, half, and go up to 3/4. Okay, so we cannot unbalance less than 50%. We have to actually balance 50% of the unbalanced force. And this is actually the resultant. So mathematically, we have to get the unbalanced force value by finding out this. Okay, square root of 1 minus C mr omega square cos theta whole square plus C into mr omega square sin theta whole square, root of that. Okay, this is the resultant. Now, coming to the next part, you see, let's read this out. The method to balance the method to balance the disturbing effect of a reciprocating mass. Okay, disturbing effect of reciprocating mass is equivalent to balancing a revolving mass located at crank pin by a counter mass added diametrically opposite to the revolving mass at the same value of the radius. Okay, so let's look at this. To balance an unbalanced reciprocating mass, what to do? By adding a mass with the same radius of this is the radius r, no, the same radius at r, so equally and opposite, sorry, this mass has to be added opposite to the mass here. Okay, that is what is said. Okay. So here you see revolving mass at the mass located at crank pin by a counter mass equivalent to a, that means what they say is it is equivalent by to adding a revolving mass at this counter crank pin. This is very difficult to scroll here and there, I'm sorry about that. So let's read it once again. The method to balance the disturbing effect of reciprocating mass, it is understood, is equivalent to balancing a revolving mass located at crank pin. Let's draw it here, let's say. So this is the slider, this is the crank pin, this is crank pin. Okay, so balancing a revolving mass at crank pin, there is a mass at crank pin which is revolving, okay, by a counter mass added diametrically opposite to the revolving mass at same value of radius. Actually this mass, see, a revolving mass which is about the crank pin, this is the mass, sorry, at a radius r, okay, can be balanced by placing another mass at the same radius below. Okay, same value radius. That is how we can balance the reciprocating mass. Okay, equivalent to placing a mass, okay, at a distance of the same radius for a mass at crank pin. Now see, the mass at the crank pin is to be taken as, this is how we have to take the total mass of the crank pin. So that means the mass that we have to place here, where is it? Here. What is the value of the mass that we need to know? This value of the mass that we have to place at the equal radius can be given by this value, C into M plus MP. Now MP is the mass at crank pin, M is the reciprocating mass. Okay, reciprocating mass. You see, so this is the crank pin. Okay, so here we have a mass plus this reciprocating mass that we have. Okay, so the reciprocating mass, you see, only a fraction of that is balanced. So we take the fraction C multiplied by the reciprocating mass, so added to that is the mass at the crank pin. So the whole amount of mass Cm plus Mp is placed at the radius r. Okay, that is how we balance it. Okay, this is the process of balancing the reciprocating mass. Okay, so please go through it once again, and we will understand it, the application in the coming numerical. Okay, we'll discuss the numerical in the coming lecture.